Hello, I am Dorian Leroy and I will provide a quick overview of our paper titled Runtime Monitoring for Executable DSLs. First, let us look at three different models. On the left, we have a class diagram, in the middle an activity diagram, and on the right a thing conforming to the thing modeling language. Assuming one is familiar with the semantics of each modeling language, the actual meaning of the first model is easier to grasp than the meaning of the other two. A key reason for this is that class diagrams are structural models, whereas activity diagrams and things are behavioral models. The meaning of structural models is more easily conveyed by static visual representations than the meaning of behavioral models. Thus, as there are different needs to understand different kinds of models, different kinds of tools must be supplied to meet those needs. Static analysis tools are well suited to extract the meaning of structural models, as such models are by design made to be analyzed statically. Static approaches also exist for behavioral models, but they cannot cover every need for behavioral analysis and can be hard to use by domain experts. Therefore, dynamic analysis facilities allowing to observe and analyze the execution of behavioral models are required to better understand the meaning of such models. Producing an analysis while observing an execution is achieved by what is commonly called runtime monitoring. While this topic has seen a sizable amount of research in the field of general-purpose languages, providing runtime monitoring facilities for any existing or new executable DSL remains a challenging task. Yet, the very aim of executable DSLs is to define behavioral domain-specific models that can be executed, and thus analyzed dynamically and at the domain level. Indeed, monitoring temporal properties during the execution enables the definition of facilities such as conditional breakpoints, test scenarios, and test records. These are all crucial dynamic analysis facilities which can be used to better leverage the executable DSLs to which they are available. But existing approaches that are reusable across DSLs have a low level of temporal abstraction and are hardly accessible to domain experts with a limited background in computer sciences. Conversely, existing approaches offering a higher level of temporal abstraction are either entirely domain-specific or not reusable by other tools. There is thus a need for an approach combining both usability for domain experts and reusability across domains and tools. The aim of our paper is to reconcile both usability and reusability while keeping a reasonable overhead for dynamic analysis activities. To this end, our contribution is twofold. In the first time, we propose an intuitive temporal property language that can be used across DSLs to specify temporal properties on executable models while requiring little technical background in computer science. In the second time, we propose a supporting architecture that can be reused across tools to evaluate the temporal properties defined with the proposed language. We also provide an evaluation of the overhead induced by using the approach on various models conforming to different DSLs. I will now give an overview of the approach underlying these two contributions. Our temporal property language results from the integration of Dwyer's property specification patterns and of the via-track query language. The property specification patterns allow domain experts to express the temporal aspects of their properties without requiring a technical background in computer sciences, thereby bolstering the usability of the language. Indeed, the patterns rely on intuitive temporal abstractions such as temporal scopes, allowing to define when during the execution we care about event patterns, and temporal patterns that allow to define which event patterns we are looking for within these scopes of interest. The via-track query language is used to express the structural aspects of the temporal properties. This allows domain experts to manipulate domain concepts while keeping the property language domain agnostic, thereby facilitating reusability across DSLs. The resulting language is geared toward domain experts as it can be used with a wide range of DSLs and provides intuitive temporal abstractions. Properties defined by the domain expert are then compiled to structural and temporal monitors. In particular, the temporal monitor corresponding to a temporal property is obtained through a novel finite trace semantics for the property specification patterns based on quantified regular expressions, which is implemented using complex event processing. For the structural monitors, the via-track query engine is reused as is. At runtime, the monitors are deployed in a property manager which is at the heart of the proposed architecture. This property manager handles the connection between the structural and temporal monitors and all the other entities involved in the execution, such as the running model or the debugger. During the execution semantics of the DSL updates the state of the executed model. This state is observed by the structural monitors, which incrementally gather matches for their corresponding structural patterns. When an observable state is reached, as defined by the execution semantics of the DSL, the property manager is notified. This causes temporal monitors to retrieve the matches detected by the structural monitors since the last observable state. Based on these matches or absence thereof, the state of the temporal monitor is updated, potentially validating or invalidating its corresponding temporal property. In case such a verdict can be rendered, the entities listening on the temporal property are notified of its final verdict. Such entities include debuggers, test runners, or analytics dashboards. We evaluated the overhead induced by the approach on models conforming to 3 DSLs. We considered models and properties of various sizes, covering 3 orders of magnitude, and on various execution lengths, covering 2 orders of magnitude. Our findings are as follows. The overhead scales linearly with the size and the number of structural monitors in a temporal property. The main source of overhead comes from the initialization of the structural patterns. This means that the approach scales well on longer executions. On average, the overhead ranges from 121% on executions that are shorter than 1 second to 79% on executions that are shorter than 20 seconds. Overall, the induced overhead is acceptable for debugging and testing activities, but not for use cases such as live analytics. To summarize this short introduction to our paper, our contribution is motivated by the fact that providing dynamic analysis facilities that are on par with those available to GPLs is essential to foster the use of executable DSLs. However, existing approaches either require a strong background in computer science or are specific to a given domain or tool. Thus, we propose an approach that is intuitive and can be reused across DSLs and tools, and whose induced overhead is reasonable for debugging and testing activities. Thank you for your attention. Don't hesitate to read the full paper and provide us with your feedback, which is always welcome.